New notation. If you have a term and you put some parentheses around it and write the word DOM, or if you have a term and put parentheses and write the word ran, then in both of these cases you're going to end up with a term. So we read this as, when we're reading in English, we read this as the domain of, or the range of, whatever it is that's inside. So this is a term because the domain of something is another thing. It refers to a mathematical object, the domain. Now, I'll start with the semantics before I get into how to formally define things, because it's, in terms of what's happening semantically, it's actually really simple. And it'll look like we're overcomplicating things at first in terms of the formalism. So again, what I describe as the intended meaning, or the intention for what this is supposed to do, is something that does not help you necessarily write proofs. Or I mean, it might help you, it might help guide you come up with the right thoughts, but it does not actually help you make the arguments. So you will need the formalism for that. So the idea is when you take the domain of a collection of pairs, ordered pairs, like one pair, another pair, maybe another pair, then what that's supposed to be is the set that you get by extracting the first position in each pair. Extract those first positions and collect them together and put them into a set. So that's the idea of domain. And then for range, you're extracting the second position instead. So for example, one hopes that, however we end up defining domain, one hopes that one can prove that if I have a set consisting of the pairs x, y, and z, w, then one hopes that one could prove that this is doubleton x, z, a set that whose contents are the first positions of all the pairs in the original set here. Okay, now for formalism. So finally the definition. The definition of the domain of something, let me call it S, is, okay, so how are we going to do this? So to define it, I have to use pretty much this notation, right? With the curly braces in the bar, where I tell you exactly what the elements are by telling you a condition for membership. So here I have to put a proposition such that exactly when that proposition is true is when X is in what I would like the domain of S to be. So what proposition should go there? So exactly what is it that's true about each of the things that I'd like to have end up being in the domain of a set of pairs? What is it that's true about all of these things here? What characterizes them? What grants them their membership? Well, for each one of them, they sit as the first position of some pair in this list of pairs here. So that's the membership condition. To be in the domain, you have to be the first coordinate, or the first position, or the left-hand position of some pair up here. You hear that quantifier? Some. So there must exist some pair. I'm actually going to say there must exist some second position, so that if you build up a pair using what you're looking at as the first position, then that's in the original set. So there must exist some y, so that when you pair them together like this, this is in the original set, the set whose domain you're trying to take. Okay, so reading this in English, as usual, I recommend trying to read it sort of from the inside out. So first read this condition. If I do mention the bound variables, then I would read it as there exists a y such that the pair xy is in S. But Now I want to read this without mentioning the bound variable y. So there exists something such that the pair x comma that something is in S. Maybe a smoother, nicer way to read it is that x is the first coordinate of some pair in S. So pairs always have their left-hand coordinate and their right-hand coordinate, first and second. So this portion I would read as x is the first coordinate of some pair that is in S. X has a possible second coordinate, so that if it were the first and that thing were the second, then it's in S. Then how do I read this whole thing? It's the set of things that are the first coordinate of some pair in S. All right, so I'm making a big deal about this way of looking at it because this is the definition. This is what we will have to use when we are proving things about domains. And range. So for range, I find it easiest to switch the variable names here and keep this proposition the same. So of course, if I just totally swap x and y here, or if I had just taken this and then swapped this pair, the order of this pair around, that would give the same definition of range. But somehow this is easier for me to read, to think of x's as always the left-hand things and y's as the right-hand things. Sort of imagining that these are like points in an xy plane or something like that. Okay, but it doesn't matter. So the way to read this then is that over here this says there exists it says that y is the second coordinate, so just this part says that y is the second coordinate of some pair that is in S. And then this whole thing says, or refers to, the set of things that are second coordinates of pairs that are in S. And finally, the LaTeX. So if you just type dom parentheses S while you're in math mode, so kind of like between dollar signs, then it's not going to look right. It's going to look like variable d times the variable o times the variable m. You know, it'll just be spaced all wrong. So to fix it, it would be better to make the word dom be kind of a printed as text. So here's a simple way to do it. Text. So this is assuming you're inside math mode. So you're inside the dollar signs. Then you can do this. So put the dom inside these text, the word text. This will work. Another thing you can, if you want to really do it better, instead of text, you could use operator name. Operator name. And this will allow LaTeX to know exactly what is the best way to space this relative to parentheses and equal signs and other things. So it's a subtle difference, but this is probably the better way to do it. And if you don't want to keep typing this \operator name dom every time you want to take the domain of something in your writing, then somewhere early in your document you can define a command. So somewhere early in your document you can say new command, and then this takes 2 arguments. So you can call it \dom and then just put the name of the command there. I just realized it's easier to just show what I mean rather than trying to write out the LaTeX by hand. So if I just write dom s like this, then you see it doesn't look right, right? This is typesetting it as though it's d times o times m. But if I do text, like that, this one looks much better, right? And then even better is if I used operator name. And if I want to avoid typing that, all over the place, I can go to an early portion of my document and just create a new command. Let's call it \dom or whatever you want to call it, and then just make it be this. And now if I just do \dom, then that works too. And you can do a similar thing for range, which I just did here. Okay, next I want to see that the semantic interpretation really is what we end up with from this formalism. Like if I just have a list of very few pairs, a little tiny list of pairs, does the logic of the existential quantifier here and the way I wrote this, does it really work to make the domain be a first position, first coordinate extractor? So let's suppose that S is this list of 3 pairs, AA, BC, and AD. Then I claim that the domain of S is A consists of A, B, and that's it. I don't have to say A again. Of course, it's harmless to say A again, but that doesn't do anything. So I think that this is what I get when I extract the first position of each pair. So let's try to prove this, which means let's try to see that this definition actually works, that it operates the way it's supposed to. So this is an equality, so there will be 2 directions for the proof. So there's sort of 2 subclaims, one inclusion and the other inclusion. So for this one, consider any, let's call it Z, in the domain of S. Z has not been previously used for anything, so that's fine. Then my goal is to prove that Z is in here, which means my goal is to prove that Z either equals A or equals B, according to the definition of Doubleton. Now, how do I make use of Z in domain S? There's only one way. I have to use the definition of the domain of S. So to make use of this definition, let me write out what's in here, but with Z in place of the X. So then there exists a Y such that the pair ZY is in S. So you see how I used axiom 5 there? I'm basically writing this, but with Z in place of the X. Now, how can I make use of this? Existential instantiation, right? That's how we make use of existential statements like this. So then we can get, so there exists a Y that does this, so we can get one. Let's call it Y. We don't have to call it Y, but let's. Then we can get a Y such that the pair ZY is in S. Okay, now the pair ZY is in S, and S is this, maybe you could call it tripleton, 3-element set, something like that. So S is basically the sort of thing defined here, definition 18, part 1. To be in S is to be equal to this thing or this thing or this thing. So to make use of this, to unpack this, I have to use that definition of that notation. So then, let me make some more room here, get to that inclusion later. Then ZY either equals AA, or it equals BC, or it equals AD. That's using axiom 5 on this membership. So there are 3 cases. So someone asked earlier whether you can have case splits that go to more than 2 cases. You can when you have an OR that has more than 2 things in it. So while the original proof by cases rule only talks about 2 cases, if you have a longer OR in your chain of ORs, then you can have more cases. So case 1, suppose that this one is true. Let me fill in the other cases. All right, and now in each case I want to reach my goal. What was my goal was I'm trying to prove this inclusion here. So my goal is to go from z is in the domain of S to z is in the right-hand side here, which means my goal is to prove that either z equals A or z equals B. So in each of these, I hope that I end up with either z equals A or z equals B. Now here, I have the pair zy equals the pair AA. To make any use of this, I should either use the definition of ordered pairs, or better is use the essence of ordered pairs theorem. So that's down here. Two pairs are equal if and only if the firsts and the seconds match. So from here we can conclude that z equals A and that y equals A. And I really only care about the z equals A part. So that's worth referencing, theorem 39, since that was hard work to prove that. Then by theorem 39, z is A. So z is A or z is B. So z is in the doubleton, AB, which is what I wanted. So this is the ultimate goal that I want to end each case with. And then hopefully you can see how to finish the cases. Maybe I won't write it. Here again, you would use theorem 39 and be like, well, then z is z equals B. So z equals A or z equals B, so it's in the doubleton. And then here, z equals A again. So these are pretty easy to fill in. Okay, that's for that inclusion. So you saw how that existential quantifier and the essence of pairs, theorem 39, helped us prove that what happens when we take the domain here is that we extracted the first positions. Let's look at the other inclusion and see how that's different. It's going to be logically quite different because we will be in a position where we're proving an existential quantifier rather than using one. So let's work on the other inclusion. So I'm going to consider any z in there and then try to prove that it's in there. So consider any z in doubleton AB. Now to get anywhere from here, I have to use the definition of doubleton. So that tells us that z is A or z is B, right? So then we get a case split. Case 1. Suppose z is A. And by the way, I'm not using new numbers because I'm sort of thinking that my numbering for the cases has been reset since I'm in a different part of the proof. So the proof of this inclusion up here is like a whole different thing that I'm proving compared to this part. This is like a separate proof. So I'm not calling this case 4, case 5, case 6. So my numbering has been reset. And case 2, suppose that z is B. And in each case, we want to end with victory, where victory means prove that z is in the domain of S. So that's the goal. Okay, so let's break down our goal, since our goal is kind of complicated now. So it'd be nice not to just do it in our heads. Our goal is to get to z is in the domain of S, which by axiom 5, that means our goal is to prove that there exists a y such that the pair zy is in S. Right? That's what we get when we apply axiom 5 to this definition. So the axiom 5 says this if and only if this. So now we're trying to prove an existentially quantified statement rather than using one. How do you prove an existentially quantified statement? The technique is called existential generalization, but that's an overly fancy term for something actually quite simple. If we want to prove there exists a y, which is purple, then we should just find something that is purple and then show it to the reader of our proof. So just produce one, find one, be like, here it is, here's one, here's an example. So now we know one exists. So here's the goal, sort of stated in simpler terms, is to find, keyword find, a y. You want to show there exists a y that does this? Find one. My goal is to find a y such that this is true. So this happens every time your goal is an existentially quantified statement. The goal is to find something that does something. Okay, well, I'm in a situation where z is a, so why don't I just call it what it is? My goal in this case, how to put this? So this goal here, finding a y, this was my goal from the very beginning, regardless of which case I was in, right? That was my goal way up here, right after I considered any z in there. Now that I'm supposing z is in A, my goal is more specifically to now my goal is more specifically to do this with the knowledge that z is A. So just to write my goal in sort of simpler terms, this is now my goal. So can I find something that when I put it next to A in a pair, that ends up being an S? Well, remember what S was. S was this list of 3 pairs. Yeah, in fact, I have several choices as to what I can use. I can use A itself, or I can use D. Those are both valid Ys. So take your pick. We only need one example. How about A itself? So we have AA is an S, right? That's because of the definition of S. It's a list, and this is one of them. Actually, it's because AA equals AA, or AA equals this, or AA equals this, using the definition of the tripleton, or whatever you want to call it. So, since A something is an S, this proves that there is something such that A, that something, is an S. You see, this step is the existential generalization. It's a really simple idea, much simpler of an idea than existential instantiation, I think. But actually executing it sometimes looks very tricky, because if you don't think in a sort of goal-oriented way, if you're just working with what you have and not paying attention to your goal, it's going to be hard to get to it when this is what you have to do. You know, imagine if you didn't really understand what was going on. If you hadn't thought through the goals as we did here, and you were reading this. You go from z equals a, and the next step is this pair is in there. Why? It looks like the step is coming out of nowhere. So that's the existential generalization. Find an example of a y where it works. So here we found the right one. So this is e.g. Okay. Thus, by axiom 5, this is what it means to say that A is in the domain of S. So Z, which is A, is in the domain of S. And then for this one, it'll be the same thing, basically. So let's be lazy and copy-paste, but then also carefully go through and change things that need to be changed. So for one thing, I'm more interested in B here. And so now this existential generalization step no longer works the way it's written here. In order for it to work, I need to put a B here. So I have to put a B here, no choice there, because the y here is the bound variable. The y is getting quantified, not the b. The b has to stay here. And then I have to find something that I can put here to make this true. If I can't find anything, then I would worry. Maybe it's false. So I go back to the definition of S, and it looks like I have only one choice this time, unlike last time I had two choices. Only C works. But at least I did find one thing, C. So C is an example of a Y such that the pair BY is an S. And now that completes the proof. Okay, so the domain of this list of three pairs really did serve to extract into a set the first positions of all the pairs.